When you see an object, such as a mug, your brain naturally completes the 3D structure that is occluded from view. Here, a depth image sensor sees the front shell of a mug, which we manually segment from the table. Our algorithm reconstructs this 3D structure. Since the handle is hidden from the sensor, we may imagine the handle is to the left, right, straight back, or perhaps there is no handle. Unlike other algorithms, our plausible shape sampling network generates all of these possibilities. We will visualize the ground truth, the 2.5D depth, completions from the network, and plausible completions generated from a shape matching algorithm. In some cases, there will be many plausible completions, in which case we want similar diversity in our shape completer. Sometimes there will be less ambiguity, in which case we want all samples to be similar. Our dataset is generated from mesh objects that are rotated and translated. We compute the depth view for each shape at each pose. We also compute the bounding box, represented by 8 points. In our plausible shape sampling network, we first learn a normalizing flow to represent bounding boxes. The flow maps all bounding boxes to a Gaussian distribution. Sampling from this Gaussian and transforming back through the flow yields random box-like structures similar to the dataset. In our second step, we train a variational auto encoder. During inference, our network is a standard VAE. During training, we partition the latent space and explicitly try to predict the bounding box as a mean invariance in the flow latent space. In this flow latent space, the independent variance from the encoder maps to boxes with different sizes and poses, as we just saw. If we had not used the flow, this independent variance on the corner points directly would distort the boxes. Thus, our encoder is able to learn reasonable uncertainty about the bounding box. During training, the decoder is fed the true latent bounding box, removing some ambiguity, and thus allowing the reconstruction loss to guide the decoder into producing good shapes. When reconstructing mugs, we observe that when the handle is visible, all methods, including baselines, accurately reconstruct the mug. There is little ambiguity as to the true shape, so diverse samples are not needed. However, when the handle is occluded, other methods fail to reconstruct the handle. Our method samples completions with multiple styles of handles at multiple angles within the occluded region. Quantitatively, we compare samples from our network to a plausible set generated using a shape matching algorithm. We evaluate the plausibility of a network's completions by finding the nearest plausible shape for each sampled shape. We also evaluate how well the network covers the space of plausible shapes by finding the nearest network sample for each plausible shape. We define plausible diversity as the sum of the two. When the handle is occluded, our plausible shape sampling network achieves both better coverage and better plausible diversity. We also evaluated methods on tabletop objects from the YCB set. To create ambiguous depth images, we simulate viewing these objects through a narrow slit. Quantitatively, we again find that with a narrow slit, and therefore larger ambiguity, our method both covers the set of plausible objects better and achieves better plausible diversity. To demonstrate an application, we task a robot with grabbing the mug from a cluttered table. The clutter forces the robot to grab the handle that is hidden from view. We segment the mug and select possible grasp points from sampled completions. Our plausible shape sampling network produces handles with valid grasped locations. Without these handles, the baseline grasp points are either unreachable or do not correspond to the true mug. We set up another scenario for grasping the YCB Cheez-It box under partial occlusion. The segmented Cheez-It box is used to construct known occupied and known free space voxels in the visible slit. Our plausible shape sampling produces diverse samples, and we are unsure if a top grasp will be successful. We attempt the better side grasp. Using the baseline with low diversity and incorrect completion, the top grasp appears valid for all samples, but fails when attempted. In conclusion, we propose the plausible shape sampling network for sampling diverse yet plausible 3D reconstructions from a depth image. To evaluate the quality of the 3D reconstructions with ambiguity, we propose the plausible diversity metric.